Hello guys, welcome back to this channel, Tough Math, where math competition problems given in the past several years here and abroad are solved and discussed. As we are making this video at this time, there are now about 70 problems, math competition problems in this channel. And if you are a math contestant, then you can practice solving these problems in preparation for any upcoming math contest or competition that you intend to join. And if you are a math coach, then you can train your students or your contestants using these materials. Or you can just simply ask your students to visit this channel for their training. So, without further ado, this is our problem. We will consider only one problem in this video because the solution is a little bit longer than the previous problems that we have considered in the past. Okay, so the integers x sub 1, x sub 2, x sub 3 up to x sub 2000 are all greater than or equal to 1. And they satisfy the equation x sub 1 plus x sub 2 plus x sub 3 plus and so on until the last x sub 2000 equals 2024. Between what two values m and capital M, lowercase letter m and uppercase letter m, would the sum of squares of the dataset lie? That is, the sum of squares xi from 1 to 2000 is between small m and capital M. Okay, first we take note that the sum of these 2000 integers is only 2024. So it is not hard to imagine that there are overwhelmingly more ones than integers that are greater than 1. Okay? There are overwhelmingly more ones than those that are greater than 1. So let xi and xj be two integers from this data set. Okay. So we consider two cases. Case 1. Okay, case 1, xi is greater than 1 but is less than or equal to x sub j. So this means that x sub j minus xi is positive or 0. And this in turn implies that x sub j minus x sub I plus 1 is at least 1. So we are sure that it is positive. Okay? Now, suppose we change these values. Not really the sum, but we change these values in such a way that we subtract 1 from the smaller value and add the same thing the same number to the larger value. So we let y sub I, the new value, be equal to x sub y, the smaller value, and subtract 1 from it. And the other value, y sub j, is equal to the larger value plus 1. So note that their sum is unchanged. That is, y sub I plus y sub j is equal to x sub I plus x sub j. However, okay, I will just move it here. However, the sum of squares gives a different result. Okay, so we have y sub I squared plus y sub j squared is equal to x sub I minus 1 squared plus x sub j plus 1 squared, and this is equal to x sub I squared plus x sub j squared plus 2 times x sub j minus x sub I plus 2. And since we can further rewrite this as x sub j squared plus x sub, 2 times x sub j minus x sub I plus 1. And since x sub j minus x sub I plus 1 is greater than or equal to 1, then the whole expression is greater than x sub I plus x sub I squared plus x sub j squared. So although the sum of the new values is the same as the sum of the original values, the sum of squares now decreases. Okay, when you do that, when you subtract from the smaller and add it to the larger, you can see that by looking at this simpler or smaller data set. Okay, to see this, consider the data set 1, 1, 1, 2, 3, 4. Okay, so suppose we make this table. These are our x sub i's, original x sub i's is R1, 1, 1, 2, 3, 4. Okay, and the sum of squares is equal to 1, because 1 squared is 1 plus 1 plus 1, and then 2 squared is 4, so you have 4. 3 squared is 9, so you have 9. 4 squared is 16, so you have 32. Now, if we change if you consider 2 and 3, subtract 1 from 2, then you have 1, and then add the 1 to 3, so you have now 4. So you have 2 fours now. And then when you get the sum of squares, you will have 1 plus 1 plus 1. There will be 4 ones now. And there will be 2 16s plus 16s. So you have 32 plus 4, that's 36. So when you change as suggested above, no, we subtract from the smaller and add it to the larger, the sum of squares increases. So from 32 we now have 36. Okay. Now to go directly to the point, no? So let us just make the next 4 equal to 1 and add the 3 that we are subtracting from it to the last 4. So we will now have 1, 1, 1, 1, and then another 1. Then the last 4 now becomes 7 because it takes in 3 from the previous 4. So we now have 1 plus 1 plus 1 plus 1. So we now have 5 ones. 1, 2, 3, 4 plus 1 plus the square of 7 is 49, which is equal to 54. So that's it. No, if you keep on doing that whenever you encounter two integers, one of which is greater than 2 but smaller than another one, then you change the smaller one to 1 and increase the other one by adding 1 to it. So if we keep on doing as suggested above, that is adding from subtracting from the smaller and adding it to the larger, we eventually would end up with a data set that is all ones, that is all ones except 1. That is, okay, so if we call the new values y sub I, then that we now have y sub 1, y sub 1 equals y sub 2 equals, and so on until the second to the last, which is y sub 1999. All of this equal to 1, and the last one being y sub 2000 is the only value which is greater than 1. And since the sum is 2024, then y sub 2000 must be 25. Okay? Therefore, the upper bound m m is attained and we have And we have m equals the sum of y sub I squared from 1 to 2000, which is equal to the sum of the y of 1099 ones. So this would be 1, okay, 1 squared from 1 to 1099 plus okay, this is a separate sum plus 25 squared. So the first sum is just 1099 plus 625 equals 2624. So this is the upper bound. Now, we look at case 2. Here, our xj is greater than x sub I but by at least 2. So this means that when you multiply both sides by -1, then you have xi minus xj is less than or equal to -2, which in turn gives us x sub I minus x sub j plus 1 is still less than -1 or less than 0. So it's negative. So this quantity here is negative. Okay, now. So this time, instead of adding or subtracting from the smaller and adding it to the larger, we change the values by doing the reverse. Let y sub I be equal to x sub I plus 1. So instead of subtracting from the smaller, we add 1 to the smaller. And then from the larger, we subtract 1. So it's the opposite of case 1. No? So y sub j is equal to x sub j minus 1. Again, the difference, there's the sum of the original and the new values is the same. No? So note that y sub I plus y sub j is the same as the original x sub I plus x sub j. But the sum of squares, again as before, gives something different but not the same as in case 1. Okay, so we have y sub I squared plus y sub j squared is equal to x sub I plus 1 squared plus x sub j plus 1 squared. And this gives us x sub I squared plus x sub j squared plus 2 times xi. This one here is minus. So this one here is minus 1, not plus 1. Okay. So minus 2xi it's the other way around. Sorry, it's the other way around. This one is plus 1 and the other one is minus 1. Okay. So this is minus 1. So therefore, we have 2xi minus xj plus 2, which is equivalent to x sub I squared plus x sub j squared plus 2 times x sub I minus x sub j plus 1. Okay. However, we learned from above that this quantity here is negative. Okay? This is negative. This is less than 0. Therefore, this is less than y sub I squared. Sorry. This is less than x sub I squared plus x sub j squared. Okay. So, if we do the reverse of case 1, the sum of squares decreases. So we see that the sum of squares decreases. And if we keep on doing this, we would eventually end up with a data set whose range is small. If the final data set if the final data set this data set is can be arranged as an arithmetic progression with the smallest common difference we get the smallest possible lower bound, smallest possible sum of squares. Now, however, since our data set is overwhelmingly, since our data set consists of overwhelmingly overwhelmingly many ones. Actually, more than 1,500 of them. We eventually end up with a data set not but with the data set consisting of ones and twos. That is, for I equal to 1 to 1,000, 2,000 I mean, y sub I is always between 1 and 2. That is, no value, no y sub I is greater than 2. So we let n be the number of ones and t be the number of twos. Then we have the equation n plus t is equal to 2,000 because there are 2,000 integers, and n plus 2t equals the sum of the integers, which is equal to 2,024, from which we obtain n equals 1,976. So I said earlier there are more than 1,500 of them. Actually, there are 1,976 of them, and only 24 twos. Thus, small m is equal to the sum of squares of this new data set is equal to 1 to 1,976 of 1 squared plus the sum of the square of 2, 1 to 24, And so we have 1,976 plus 24 times 4, which is 1,976 plus 96 equals 2,072. Therefore, we have M is equal to 2,072, which is less than the sum of squares of the original data set. Okay. But this original sum of squares is less than or equal to the data set where all except 1 are equal to 1. So this is 2064, I think. What is that value? 2,624. So we have 2,624, and this is our capital M. So that's it for this problem and for this video. So the lower bound is 2,072 and the upper bound is 2,624. Okay, so before I go, I leave this challenge. How many triples of positive integers x, y, z where 1 is less than x, but x is less than y, and y is less than z, satisfy the equation 1 over x plus 1 over y plus 1 over z equals 1 over 2007. So I hope you enjoyed our discussion for today. You learned something new, and I hope you will continue viewing the problems and learning from them, problems in this channel. So that's it, and goodbye for now, and may God be with you all.